With this one, the answer is E. We have actually met all conditions. And the way that we can kind of reason through this, there are three conditions that need to be met in order to make a confidence interval an appropriate thing to do. It needs to be random. And it is fair to say that this is a random selection of people because they were selected through a random method. So you can see right here, it's a random number generator. So it is random, 10%. Well, now let's jump into the sample size, because if the number was picked between 1 and 100 and 50 was the magic number that made you included, there's a 1 in 100 chance of that happening. So 1% of the people will have been chosen for this sample, essentially.
There's no guarantee, is there?
There's no guarantee, but it's going to be close to that. Long run probability. Since there's 50,000, it's going to be close to 1%. So 1% of 50,000 is 500. Sample size is 500. So in this case, is 500 less? Well, we know it's 1%. So yes, it's less than 10%. And then the last part we can assume right here, if 30% was our p hat, it's going to be 500 times 0.3, and then 500 times 0.7, and we'll get our answers there. It's going to be 150 and 350. And obviously we have met the normal condition for proportions. So at this point, yes, we've met all conditions. Now it's worth mentioning here, and this is something that there's some nuance to the 10% rule that I haven't taught very well. In this case, we are sampling from a finite population without replacement. So whenever we sample one person, they can't be selected twice, all right? In those kinds of situations, even with a huge population like this, but in those situations, you need to make sure you're using the 10% rule to make sure you're not selecting more than 10% from that finite population. But if this was a question about basketball throws or shooting an arrow at a target, there really is no population for that because each trial is independent. So when events are independent, you don't need to worry about the 10% rule. In fact, what you need to say in that situation is, because these trials are independent, each die roll is independent, each arrow shot is independent. Because of that, the 10% rule is not applicable. And that's something I want to kind of start emphasizing and re-emphasize as we head into the AP test time, which again is May 25th. And yeah, there was something I was going to mention about the AP test, and it just has to do with logistics. I'll talk about that whenever we're signing in. So let me just clear this out.
I will answer every.
Okay. Okay, we'll hold you to that. So today we're going to do some review of Unit 3 and 4. Unit 3, well, let's just jump into it. So we're actually not going to be talking about the FRQ I assigned last night, and I accidentally didn't provide that FRQ for a while. So if you tried to access it right after school, you might have run into some difficulties or whatever the case. I'm sure it was. So I fixed it now. So at this point, if you want to access that, just have a look over on that before next Monday. Okay, tonight's FRQ is set up and ready to go. Why does it say Unit 1? Oh, we're not doing this. Wait a second. We did that yesterday. We already did this stuff. Unit 3 review. Okay, sorry about this. Unit 3 review. This was dealing with scatter plots and, of course, regression. So that meant your regression equation. This is on your AP formula sheet. DUFs, which is direction, unusual features, form, and strength. So those are the aspects of your scatter plot that you want to be able to describe. All right, there's a correlation coefficient and your coefficient of determination, your R squared. And remember, your interpretation of your R squared is that this is the percent of the variation in your response variable that can be explained by the model. All right, so higher that is, the better. Your correlation coefficient is the strength of the relation between the two. Now, it's just kind of weird that we have R and R squared when it seems like both one would get the job done, but it's stats. There are mathematical reasons for that. Okay, a field researcher who studies lions conjectured that the more time a cub spends playing, the sooner the cub will begin to hunt. Observational data were collected from 20 lion cubs. The researcher recorded how long they spent playing and the age when they began hunting. Because male and female lions have different hunting behaviors, the researchers recorded the data for males and females separately. 2 scatter plots show the data for the 10 female lions and the 10 male lions. Now, I wonder how they tell the difference between the two, because they're probably not just getting right up to the lions to find out. But anyways, there you go. You got a couple scatter plots. Based on the scatter plots, for which gender does there appear to be evidence that the more time a lion cub spends playing, the sooner the cub is likely to begin hunting? I probably won't read all these, but there you go. So we are asked to interpret 2 scatter plots and determine which one shows a relationship between the time a cub spends playing and the sooner the cub, and the length of time until they start hunting. Now, I will say this. It's maybe easier to kind of think about this in terms of, create your own scatter plot right here. As playtime increases, the time to first hunt should decrease. So we're looking for a negative relationship between these two. So as one increases, the other decreases. The only one that shows a negative relationship is female. Male looks to be no association at all. Okay. So there we go. Looks like the answer will be D. So it looks like males start hunting at about 13 months regardless. The females can start anywhere from 16 down to 12 months. All right. We'll clear that. Let's look at the next one. For a random sample of 20 professionals, well, I'm not going to read it, sorry. But you can read through that and see if you can figure out the best answer. So my thought process going through this, and yours doesn't have to match mine, but my thought process is with this sentence right here, starting with that one, it tells me that as exercise increases, so I'll put E for exercise, as that increases, heart rate goes down. So this is going to be a negative relationship. It's going to look like this, and that means it's going to be a negative correlation. So in that case, I can rule out these. Now, a perfect correlation is very, very, very unlikely. So I wouldn't lean toward that one. So the question is, should it be negative 0.87 or negative 0.14? And what lets me know that it's negative 0.87 is that it says right here in the first sentence, there's a strong linear relationship. So negative 0.14 would be very weak relationship between the two, but the negative 0.87 tells me, with my correlation coefficient, tells me it's going to be a strong relationship. All right, so the points on this one probably cluster around like this, as opposed to your negative 0.14, which would not look very much like an association at all. All right, next question, I'll let you read through this. Okay, this entire question, once you read through this, is dealing with the idea of extrapolation. And we can see that the actual lengths from our data vary from 0.75 to 1.35. So we're going to have a scatter plot. So it's estimating the weight based on length. So we're going to assume there's a positive relationship. But here's our data right here. And they're saying, what if you had 3 inches on this fish? Could you estimate the value? But that would not be appropriate because this far exceeds the maximum value of lengths in the sample. So E is the answer here. And it's basically saying don't extrapolate, that's bad. Okay, again, a conceptual question. It has numbers in it, but really we're not doing math with this. We're using math concepts. An engineer believes there is a linear relationship between the thickness of an air filter. I'm reading it, aren't I? But anyways, you can finish reading through that and see what you think the best of the answer is. All right, in a residual plot, if there is a linear relationship, we should see
I got it.
Something that looks like this.
I know what it is.
What? Which one?
I don't know.
Oh. We should see a residual plot that looks like this. Some of them close, some of them far, but it should just be a very,
Oh, it's A.
no, in this case, we're looking for D. There should be no pattern.
Also, it said there should be.
Okay,
That's what-
okay, I believe you. There should be no pattern. Now, we do not expect residuals to be 0, and we shouldn't see any sort of these things, any actual associations show up in the residual plot.
Should
And-
the residuals add up to 0 though or something?
Well, your residuals will add up to 0.
Yeah, that's what I was thinking.
Yeah.
No, Leo, you ruined it. Looks like a bug now.
Okay, so I'm going to go ahead and move on to the next problem. I'll let you guys read this and figure this out.
Let me throw.
All right. So with this problem, we are not looking for an actual amount of milk produced at a particular age. We're looking for the difference between a cow 5 years and 10 years. And the difference, of course, is there's 5 years older for that 10-year-old cow. So we know that it's going to go from some amount of milk produced to minus 1.1 times an extra 5 years. So it's going to be negative 5.5. You would predict, what is this? Gallons per week. That is, I did not think, I don't know how much I thought cows produced in a week, honestly, but 40.8 as the y-intercept, that's a lot of cow milk. Okay, anyways, 5.5 gallons less per week for the 10-year-old cow, which means the 5-year-old cow is going to produce 5.5 gallons more.
Imagine the dude having to milk all those cows.
They get machines to do it.
Oh, really?
Yeah, it's just a milk factory these days.
Dude.
All right. Next question. Let's see how much more we have from this unit. Oh, these are some FRQs. So let's go ahead and give this one a shot. This one hopefully doesn't take as long. Because point A has higher leverage, you can see here's the data, and this is extended beyond, so that means it has leverage. It also doesn't seem to fit the rest of the trend line, so it's going to be an outlier. So that's going to affect, it's going to be an influential point. All right, it's going to change our least squares regression line. So if we got rid of it, if this is no longer there, because this is now dragging it down something like this, but without this being here, we're going to go back to that original regression line that I drew in the solid. So the slope is going to increase, and the correlation coefficient will increase as well, because all of these squares of our residuals will be much smaller, the sum of the squared residuals. So the answer is D.
Oh.
Okay, good job, everyone. Okay, here we go. Oops. Well, something happened. There we go. Let me go ahead and. So what we are looking at here is, well, I mean, it's just, there could be any number of correct answers to this question, but based on the 5 that they give us, what we're looking at is either the correlation coefficient or the coefficient of determination based on how things are being presented to us. So the correct answer is C. Let's just jump to that. And the proportion of variation in height that is explained by regression on age is 0.64, because our R squared value is going to be 0.8 squared, which is 0.64. And like we were talking about with coefficient of determination, this is the percent of the variation in our response variable, in this case height, that is explained by the explanatory variable, which is age, or is explained by the model. Yeah. And so since B was the answer that was chosen, I want to remind you that the slope of a regression line is not B. The slope is, or it's not R. It's not, sorry. The slope is not R. It's R times the standard deviation of Y over the standard deviation of X. So the correlation on its own does not determine the slope, but the correlation is a factor of the slope. It factors into the slope. All right, here is an an FRQ. All right, we can look at this real quick. Maybe just verbally go through this one. We won't necessarily stop and answer it, or stop and take tons of time with it. After point P on the graph was removed from the data, a second linear regression was performed, and we see the printout with P included and a printout with P not included. Does P exercise a large influence on the regression line? And explain. So with this question, I'll just verbally talk through it. We're looking at these variables. So this has a regression equation up top of y hat equals 0.4, well, sorry, it's a plus bx. So it's going to be 8.107, which is our intercept, which is the constant, plus 0.4919 times x. This one has a regression equation of 11.123, oops, plus 0.15 times x. So are these two equations very different? Yes, they are different, but another thing we can look at, that's one way of referring to this. We can refer to this, we can answer this question based on the fact that our regression line has changed a lot. The slope has changed quite a bit, the y-intercept has changed, but another thing that's changed is this r-squared value. In the first one, this 1 point gave us an r-squared value of 48%. But that was an artificial r-squared based on 1 point because the rest of the relationship only has 2.5% r-squared value. So is this a large, does this have a large influence? It absolutely does, because now only 2.5% of the variation in y is explained by the variation in x. Okay. So the next one, next part says, now pretend that P was actually recorded incorrectly and it should have been shown at Q. Explain how the least squares regression line for the corrected data would differ from the least squares regression line in the original. So in the original, P was way up here, and that was an influential point. Notice the X difference in for P and for Q. P is the incorrectly recorded point. Q is the correctly recorded point. But both of them they are high leverage. So in this case, it gave us that. Now with Q being in the right spot, maybe it's going to look more like this. So what would we describe? We wouldn't worry about specific numbers here, but we would say now it's going to have a negative slope. It's going to be an influential point and an outlier. It's going to be high leverage, this point. We could say that it's still going to have low association, but it's going to have an artificially high r-squared. And anyways, there's basically no association unless we have this 1 point there. And then it creates what seems to be like a stronger association. So exactly how you want to answer that, I know this isn't the most robust kind of review of this, but however you want to kind of phrase that, those are all different ideas that you can include. Are there questions on that? All right. As we get closer, I'm going to give you guys some practice exams. This is just reviewing all the content, kind of quick and dirty. But when we get into kind of this time period between the end of our review and the AP test, I will be assigning those of you doing the test more FRQs to kind of look through and kind of take the time to answer. And that's what you have available every night as part of your homework. So now let's jump into Unit 4. This is all about your experimental design and talks about sampling methods. So you've got your simple random sample, your cluster sample, stratified, systematic. When I say all those terms, do you guys know what all these mean? Of course. Okay. So let's say you're an alien coming to abduct people. Yeah. And you want to randomly sample across the globe. You can just pick a random coordinate and that is what you would do. Just, I want to abduct 100 people and now I'm just going to get 100 coordinates, make sure they land on land, not in the ocean. 100 coordinates, And I'm just going to go there. They might all be in Texas. And maybe we should have more people abducted from Texas, so that would be a good thing. But they might be scattered across 100 different countries, whatever the case. Cluster sampling. This is if these aliens had a reason to believe that the United States was representative of the rest of the world, then they could just sample maybe everyone in America or sample only from America. And then they could say, these people in America are representative of the entire world. And boy, would they be mistaken. But that would still be the idea behind it. And another way of looking about this is like, remember the idea with the lasagna is that if you just got a chunk of lasagna like you would normally serve yourself, that's a cluster sample because you're going to sample all the different parts of the lasagna. Stratified. Now, with stratifying, let's say there is reason to believe that humans on the different continents were different from each other in strong ways. So you might say, I want to get a cross section of the entire human race. So we're going to make sure we randomly sample and we get at least 5 people from Asia, at least 5 people from Europe, at least 5 people from Africa. Man, I'm really stretching this abducting aliens thing quite a bit, but it's working out. 5 people from Australia, maybe 5 penguins from Antarctica. I don't know. There are people down there. But anyways, you could stratify based on geographic location and make sure you get a representative sample from all the continents.
5 people from all over.
What's that?
You know, all over.
Oh yeah, Hollow Earth. So maybe I haven't been. Systematic sampling is, let's say that maybe we'll still pursue this from the alien perspective. Let's say you have a list of all the people on Earth, and you just decide every millionth person is going to be the one that we abduct. I've got a list. I'm going to start with this person randomly. I'm going to count 1 million down. I'm going to sample that person, 1 million down, and then you do that until you got your 7,500 people in your sample.
We try to run these back. So simple random sampling is just like completely random. Just like maybe it'd be like.
All right, there are, even beyond deciding how you're going to pick people, there's different kinds of bias that exist. Maybe you accidentally exclude people from even being selected, like people who live in very remote places. So maybe they're just completely not included, so that's under coverage. Convenience and voluntary response sampling. Maybe you just are like, well, we're really close to this location, so we're going to abduct whoever is close to us, even if that's not the appropriate person to abduct. Response and non-response. Non-response would be if someone doesn't respond to the survey, and response, like they are included, but they just don't even respond to it. Response bias is anything that someone does respond, but it can affect how they respond. The wording of questions, your nonverbal communication behind it, whether it's a face-to-face questionnaire or an anonymous response. So many things can affect it. Anything that affects how someone responds to an answer is response bias. Sampling bias or sampling error is not a negative thing. It is a natural part of a sampling process. And the idea behind it is that we want to get a sample that is representative of the population. But sometimes our random sampling, we just get kind of an extraordinary group of people that are very extreme in one way or the other. That can happen. And so the goal is that we want our sample to match up perfectly with the population mean, the population average. But it doesn't always. So that's why, our sample might be down at the lower end. Observational studies, we do not randomly assign, but we're basically observing people's behaviors without randomly assigning them to a task or to a treatment, I should say. So if you're just trying to examine how certain behaviors affect people's health, maybe you just look who are smokers, who are not. You're not assigning someone to be a smoker, but you're going to observe this is their health outcomes because they smoke. Experiments involve random assignment, and in sampling, if you want to make sure that you are controlling for different factors, you can block. So maybe you think males and females or any variable, any characteristic difference. You want to make sure that you're controlling for that. So you might say, I'm going to have an equal number of males and females, each getting different types of treatments. So you block first, you split them into males and females, and then you randomly assign within those blocks. It's the same as stratifying, but it's a vocabulary thing. When it's an experiment, we're blocking. When it's in a sample, we're stratifying. Treatments and levels. So you can have treatments of like getting the actual drug or getting a placebo, and then maybe even getting the drug that you're testing would have different levels. So when we were talking about all the trials for getting the COVID vaccine, well, they had to have placebos, people who got a fake shot. Well, and actually there was an ethical thing. And in medical stuff, there's always ethical stuff. And never mind, I won't say things. But there was this ethical thing where whenever they first started coming out with vaccines, and they were like, hey, it's 95% effective, right? The question was, and they're trying to figure out, okay, well, who gets the vaccines first? Well, some of the people who were involved in the trials who got the placebo were saying, listen, I put my life on the line. I got a placebo, but we didn't know if this vaccine was actually going to have side effects that would be really detrimental. So because I was willing to risk my life on this, I should be able to get the vaccine first. This isn't directly related to our unit review, but it is an interesting thing if you get into anything related to this in the future. Ethical issues come up. I'm sure by now they have, but I don't know how. And remember, it was all rolled out state by state. So certain states might have done something like that. And in Arizona, I don't know what they chose. Okay, so here we are. We've got some questions from Unit 4 I want you to look at. We'll just go through a few of these. Okay, so because the population that this was selected from were only teachers at this conference, the only thing we can generalize this to is the conference attendees.
Really?
Yep. So the answer is B. The sample is the 50 conference attendees, but the population is the conference attendees. If we wanted it to be all the teachers in the state, we would have had to randomly sample across the entire state. I can tell you a lot of teachers don't go to teacher conferences. So yeah, those are, do I?
Yeah.
No, no, I don't. I take my summer off. All right, here is another question related to statistics. All right, so after looking at this, the problem with this sample design is that this school newspaper reporter is talking with students who are leaving the cafeteria, and it says at the very first sentence, students can choose whether to eat in the school's cafeteria. So there are a lot of students who are not choosing to eat there. So any results that she gets is coming from a subset of the population, students who are eating there, and 89% of them are happy with it. So maybe there would be fewer people happy with it if it wasn't right here, B, self-selected students, and if it was representative of the entire school, they could get a better result. Okay. Good question. So we're asked for finding an example of non-response bias, and the answer is B, because these are people selected to participate and they don't participate. So that is the very definition of non-response. The first one, this one, and this one, so those three are response bias because they did respond, but not in the most accurate way. And then this is an example of under coverage. So they were not even included in the sampling process at all. So I will bring up another question. I can say the good thing is that everyone kind of answered this one correctly. Now, not everyone got the right answer, and honestly, I can't remember which one I said. I might have even put the wrong answer in when I answered. But because this is an experiment, we are blocking, but blocking based on dog breed is the best choice right here. I might have put C as I was answering, but stratifying would be if we were sampling. Blocking is whenever we're setting up an experiment, and this is an experiment, and even it doesn't, well, no, it does say an experiment right here. So you can look out for that, or at the very least, words that basically mean the same thing. Okay, so the answer is B.
Wait, say it again. So block is for an experiment.
Yeah.
What would be stratifying?
Stratify would be if you were sampling, like we want to find out if dogs have fleas, and or like what proportion of dogs have fleas, and then you decide we're going to stratify. I want to test golden retrievers, and this and that, like split
so
up.
not actually giving them like treatment.
Yeah, there's no treatment. It's just testing to see, based on this question, do you have fleas? Dog, do you have fleas? But then blocking is like we have a treatment. We want to give you the new formula or the old food formula, and we want to make sure that we split by dog breed first to see if within a breed the new formula helps growth in the dogs. Okay, good stuff. It's all made with leftover meat anyway. All right.
This is nice because like I feel all the examples that you talk about, I'll remember on the test. Like I'll remember the alien abductions.
There you go.
Different types of samples.
I hope that does help.
Yeah.
Okay. All right, let's look at this one. Okay. Now this is a little bit more conceptually, what's the word? A little more deeper conceptually than the previous questions, perhaps. Now you can have an experiment. This is an experiment because she is assigning treatments randomly. The question is, so it's not an observational study or a census, but the question is, okay, what kind of experiment is it? Matched pairs, block design, or completely randomized design? So the water is, what kind of water, like the regular water or having the new powder? Those are the treatments. All right, we have to understand those are the treatments that we're going to get response variable from. So it's not blocked right here. So maybe it comes down to, is it a matched pairs design or is it completely randomized? It would be matched pairs if she said, for every 2 sets that go out, I'm going to flip a coin for the first one. And if the first one gets the powder, then the second one gets the regular water. If the first one gets regular water, the second one gets the powder. But it's not done that way. It's just every single one of them gets its own coin flip. So technically the way this is done, she could end up with all of them getting one treatment, none of them getting the other. But regardless the way she set it up, it is a completely randomized design as far as randomizing who ends up with which treatment. That's the way it's done. Am I right? Statistics.
Oh, yeah. Oh, yeah,
Okay.
because you're going to see it.
Yeah. All right, let's see. We got, oh, look at this. We only have one more question, and we're going to call that good. So this experiment, the way it was set up, I'm just going to jump to the answer. If I can find where it says it, it was a group of seeds, green bean seedlings. And this experiment only included green beans, so it cannot be generalized to all vegetables. So that's basically it. If you go through everything else, I'm not going to go through all the reasons why. But replication, that's a good one to know. That's just including a lot of observational units, or experimental units, I mean. So in this case, if you had a lot of green beans seedlings and they had 200, then the more you have, the better. So replication has been part of it. So I'm not going to go through everything else. Well, maybe I will just say cause and effect can be concluded because this was an experiment. It was not an observational study. And remember, experiments are the only thing that can lead to conclusions about causation. All right, now this is one, just remember with blocking, and well, in this case, we're going to be doing kind of matched pairs or blocks of size 2. And you want to make sure within your blocks, when you randomly assign, that you get people as similar as possible. So this is a question I believe everyone had. So you've seen this before, but basically you want to, if they think age is the primary variable that matters, then you want to get the 2 closest ages together. So 1 and 2, and then within that block, you can randomly assign a treatment, one versus the other. And this is related to conditioner on your hair, or sorry, a shampoo. So anyways, you want to combine the 2 closest ages. So as you go down, here's a 23 and 24, these 2 44-year-olds, and then you have a 46 and 47-year-old, and so on. So you want to find the 2 most similar, randomly assigned within the block, and then you can move forward. The one thing I will say is that the idea of blocking is that you should randomly assign within the block. So in the part C right here, it says, the boss suggests giving 3 of the blocks the old and 3 blocks the new formulation, but you don't randomly assign between blocks, you randomly assign within blocks. So that would not be an appropriate use of blocking. All right. And that we can call that good for the day. 10 minutes to spare. There are a couple of FRQs which we will spend some time looking at tomorrow in class. And the practice test, which is just your multiple choice questions part of it, is live on Canvas, at least it should be. And that can be turned in at any point. But if you want to get credit for it, remember everything that I'm assigning now is optional. If you want to get credit for any of this stuff, make sure you get it done by May 28th. All right. All right, that's good. I'm going to stop talking at this point. Have a wonderful day, and I will see you tomorrow.
What?